Welcome everybody to another episode of Solving Infinity, brought to you by me, Colin Power of Into Infinity. Today we're going to be solving something called the Russell paradox. Now the Russell paradox was so fundamentally mind-blowing in mathematics that it's never really been solved, and it evolves around the concept of there are more infinite numbers between 0 and 1 than there are sort of whole numbers in existence. And that provides a little bit of a paradox because in a sense you could say all of the whole numbers can be contained within the space of 0 and 1, because every whole number has a reciprocal value. You can take 1 and you can divide it by 2, for example. You get a half, don't you? Yeah, that's the 2 there. You get 1, you can divide it by 3 and that create a third. But that's the 3 as well, isn't there? So it's an equivalent. That proves in a sense that there are more numbers between 0 and 1 than there are whole numbers into infinity. Is that those numbers, rather than increasing towards a so larger number, actually diminish towards 0. And that says something quite fundamental about the concept of 0 itself being a kind of infinite boundary and an infinity going inwards. And so there's different types of infinity. There's an infinity that explodes and grows larger in number, whilst at the same time there's an infinite set of fractions that diminishes towards 0 infinity. In our last post we looked at something called Aleph 0.5, where we showed that if you add up those fractions you actually produce an infinite number series that is exactly half that of the whole number series as it progresses. And so that's very interesting because that means there's a greater density of infinity in between that 0 and 1. We know that now for sure. But also we can resolve exactly how do numbers work, and we're going to do that using just a square piece of paper and a little bit of origamis. And what we're going to do is we're going to sort of just take the paper and we're going to fold it, and in doing so then we're going to open it out again, and then we can fold it again. We've actually got 4 spaces now on the page. And if I put a little 0 down here, yeah, then what we're going to have is we're going to have a +1 here, and then this will be plus infinity over here. So you can imagine this like a number line, and everything between 0 and 1, all the numbers, yeah, fall between here and here. And any number that's larger than 1, including all of the decimal fractions, will be here, right? And we're going to do the same thing here. I'm going to put a +1, and the same concept applies, yeah? So these are 2 axes on a graph. And what we're going to say is that this represents all of the whole numbers can be represented. Imagine we could make a dot there and that could represent a whole number, yeah? So it might go up like a line like that. And there might be another whole number there like that, yeah, and so on and so forth. And really, although I'm drawing these lines like that, there's an infinite number of these lines. So everything above the 1 is it has a whole number, yeah? So there's 1, 2, 3, 4, 5, up to infinity, yeah? Now, let's turn the page this way, yeah? And we've got 0, +1, and plus infinity. So every number that's above 1, every single number will appear in here. And so what we do is we say, okay, which numbers have a decimal fraction of some description? So, for example, 0.01111. So that would draw a line, and we draw a line. So these, all of this here, is we start to form 2 different types of number space. And this is all the whole numbers, yeah? And so what you see really is here is that you've got a grid, haven't you, yeah? Whereby this here, this section here is defined by a cross, whereas this is defined just by 1 line, yeah? So here's the magic, yeah? What we do is we fold number space across its axis like that, yeah? It creates a new number line through the diagonal. So we've got a new number line now which runs from there to there. It contains all of the numbers from 0, 1 to infinity, and there you can see that the difference between the 2 is the way that the lines cross on each part. Each point on this line is formed by just 1, 2 lines crossing, isn't it, yeah? It forms a cross, so we could look like that, yeah? Whereas this line here, every point that falls across there would be 1 point there, 1 point there. Let's do 1 point there, 1 point there. It's a little bit off, but you can see what I mean. And as you can see here, that 1 there, 1 there, and 1 there. And so what you get there is another type of thing. You get like, it's like a hexagon, yeah? Isn't it, yeah? This becomes a square. This becomes a hexagon, yeah? And so now what we have is a geometric model that resolves this kind of concept of the Russell paradox. How can there be more numbers between 0 and 1 than there is all of the whole numbers combined? Yeah? And what we see is it's because they can be written as a different type of dot, if you like, a different quality of something. Yeah? And everything that happens between 0 and 1 now just becomes part of this cross, whereas everything beyond 0 and 1 becomes part of this 3 points that define a single point on the number line. And so that's the concept, isn't it? That we're folding number space, and as we fold number space, so it creates a different kind of number beyond 1. So this technically solves the Russell paradox as to how you can have an infinite set of numbers between 0 and 1, and yet an infinity of infinities set of numbers, because they're different in the way in which they're expressed on the number line. So how does this help us solve something called the Russell paradox? But the most simple explanation is to take something like a piece of paper, and on that paper you write that the statement on the other side of this card is true, and then you can turn it over and you can write the statement on the other side of this card is false. I've had to sort of resolve this kind of concept that the statement on the other side of this card is true. But if I turn it over and it says, and the answer here is that the statement on the other side of this card is false, then it means that the statement here is false, not true. And if that was true, if that was false, not true, then this would have to be true, not false. And so you keep going round and round in a kind of mathematical paradox. And so whatever happens, it seems an impossible thing to answer because one answer contradicts the other. So what's the solution? Well, just as we saw with our model there, folding number space, we can do the same with the card. And when we fold the card in half, then what happens is both sides become true. And that's what happens when we fold number space. Now, at first, this might seem a little bit tricky to get your head around. Why bother doing all of that? But once we begin to understand the structure of number space, which is what we'll look into next, then all of this mathematical solutions to these paradoxes which have never been resolved starts to open a doorway to a new kind of mathematical understanding. So stay tuned with us and we'll bringing you more videos very shortly. Do subscribe to the link below if you'd like to follow along with us.